Okay, so yeah, as mentioned, my talk will be about holomorphic induction for Fréchet-Lie groups, certain kinds of Fréchet-Lie groups. And please let me know if I write too small. I sometimes do that. And this talk is based on some research I did when I was a PhD student not too long ago. And you can find more details in a preprint with a certain number. Hope that one. Okay, so before starting with the holomorphic induction part, maybe it's a good idea to say a few general things about unitary representation theory in the infinite dimensional context. So generally speaking, representation theory aims to understand two things. So first of all, you usually want to classify all minimal objects, say irreducible, the minimal representations. So these would be homomorphisms into the unitary group of some Hilbert space. And secondly, if you understand all of the minimal ones, you would like to know how does a given representation decompose into these minimal pieces. So you want to understand the decomposition. Well, I wanted to keep it vague here, but let's say irreducible. Decomposition, but you can also wonder about factor representations. Decomposition into minimal pieces. I mostly wanted to convey the philosophy. You want to understand the building blocks and how other things are made out of these building blocks. So for example, for finite dimensional Lie groups, you typically want to understand how does L2 of G, the regular representation, decompose, and or maybe some homogeneous space, and that then leads to harmonic analysis. But in the infinite dimensional setting, some problems occur. So in infinite dimensional setting, we have problems. And one of them, it has to do with the fact that the group is not locally compact. And as a consequence of this, you will not have a Haar measure, of course. So you have no Haar measure. But this breaks many constructions that you usually have in representation theory. For example, you will have no group C-star algebra defined in a canonical way because you cannot define the convolution. Similarly, you have no regular representation, not the unitary one at least. No unitary regular representation. And you also have no general notion of unitary induction. And all three of these play a really key ingredient in the representation theory of finite dimensional Lie groups. So it's quite problematic that we don't have any of this. What is more, it is also typically the case that infinite dimensional Lie groups have typically have so-called wild representations. And what I mean by that is that they generate a factor of type 3. So that's right, type 3 for Neumann algebra. So the situation looks quite bleak. The main goal is to understand the minimal objects and then to understand the decompositions. But already the first one is totally intractable. So this one is totally intractable. It's usually, you cannot hope for a full classification of our irreducible ones. And for the second one, well, given a representation, you can ask how does it decompose? But there's no natural regular representation to which you may want to study. So what do we do in infinite dimensional context? Well, first let me mention that there are, of course, many representations of infinite dimensional Lie groups. Their existence is not a problem. And given one, you may want to know how it decomposes. It's just you don't have these natural. So one way out that is very typical in this situation is to impose additional restrictions. On the class of representations that you would like to study. So instead of considering all representations, I focus on a subclass. And one such condition that you may want to impose is the so-called positive energy condition. I will not define it now, but if I have enough time, I will come back to this later. And the second thing is that, curiously, the concept of holomorphic induction does generalize, even though we have no general notion of unitary induction. Holomorphic induction does generalize. Kind of a curious fact. So it historically went like this. In my PhD thesis, I was studying these positive energy representations, and it was known that holomorphic induction is a good tool to study them. And I needed a more general version that was available, and that was kind of the starting point of this research. And now I want to explain what is holomorphic induction, what do I mean by this, and how can I, what did I actually do in this work. Okay. They're more heavy than the ones incredible. Okay, so we get to the second part about holomorphic induction. But maybe it should be clear by now why I want to study this. It's one of the few tools available. So of course you want to study it. And also it turns out to be very powerful. So what is the rough idea? Well, the situation is as follows. You want to start with a closed subgroup. So this will not be very precise yet. I will make it more precise in a minute. Closed subgroup. So given a closed subgroup and a representation of this closed subgroup on a Hilbert space V sigma, I want to say something about some kind of induced representation. And usually induced representations have to do with sections of associated vector bundles. But now we want to do something with holomorphic induction. So the idea is to equip the homogeneous vector bundle this homogeneous vector bundle, we want to equip it with a complex bundle structure.
Bundle just means a vector bundle over homogeneous space?
Yeah, but with a transitive action of G also. Yeah. Okay. So there is a transitive left action covering the left action on the base. And you wanted to preserve the structure of the fibers, in this case, that of Hilbert space. Okay, so to equipped it with a G-invariant complex bundle structure. And then you want to consider holomorphic sections of it. More specifically, you want to look for some kind of Hilbert space sitting inside these holomorphic sections. I will denote it by like this. But it should be sitting in there in a good way that I will make precise like in a few seconds. And in that case, this should be a G-invariant. So this space is G-invariant because the complex structure should be G-invariant. And then we are looking for a G-invariant Hilbert subspace of that, on which you then have a representation. And that will be called holomorphically induced from the one we start with. But now I want to make it more precise.
You mean that the action restricts to H?
Yes.
Okay.
So now I want to make it a little bit more precise. So what is actually known? And now I go to the infinite dimensional context, and I want to describe it in a setting where G is a Banach-Lie group. What I'm about to describe now, it has later been generalized a little bit to some case where G is allowed to be Fréchet as well. Okay, and this closed subgroup H should be a closed split Lie subgroup. So it is an embedded Lie subgroup, and split means that its Lie algebra is complemented. So, by the way, I will denote this by this math-frac. Okay, and then we have a representation, as I said, of this subgroup. But in the setting that was known before, this is always assumed to be continuous in the norm topology. And this is a very restrictive condition. It is quite rare for a representation to be continuous in the norm topology. In fact, since this is now a Banach-Lie group, and this as well, it implies that it is smooth. So this will actually imply that this is homomorphism, a smooth homomorphism of Lie groups. And in particular, that further implies that the derived representation, not only does it map in the bounded operators, it is also a bounded map of Banach space. Okay, I just wanted to emphasize this restriction because that is kind of what I want to remove later. Okay, so now we want to make sense of these complex structures. And there I want to mention also what has been done. So it turns out that the G-invariant complex structure on this homogeneous space, that corresponds to closed subalgebra E of the complexification of G. So it should be G-invariant, so it kind of makes sense that it should be determined by what happens above the fiber, like the identity coset. So it makes sense that you should be able to describe it in the algebraic terms. But not just any closely subalgebra, a particular one, it should satisfy the following conditions. So we want that its intersection with this conjugate is the complexification of this H. We want this condition, and finally it needs to be invariant under the H action. Okay, and this for the finite dimensional case was already known for a long time, and in the setting I'm describing here, there's a paper by Daniel Beltita, in 2005, where this is shown, this correspondence. So that kind of helps us understand what these complex structures are on the homogeneous space. And then we still need to know what is the extra data that you need to add to get a complex bundle structure here. And that has also been studied. So then a G invariant are compatible with the chosen B, compatible the invariant complex bundle structure on this homogeneous space then corresponds to providing an extension of, okay, I'll just write it, of the derived representation that you induce from. And it should have some compatibility relation with respect to this adjoint action. So you want to have that psi at H is okay. So this is really a one-to-one correspondence between compatible complex bundle structures and such extensions. And this is done by a paper in 2013 by Milan Niestijl. Okay. So then what in this situation is the precise definition of holomorphic induction? We say that a unitary representation, the D representation rho acting on some Hilbert space H rho, is holomorphically induced from the representation that we start with together with this extension specifying the complex structure. If, well, as I said, we want our Hilbert space to sit in a G equivariant way inside of the holomorphic vectors of this now complex vector bundle. So I use this extension to equip this with a complex structure, and then I can look at its holomorphic sections. And before I said it should sit there in a good way, what did I mean? Well, this means that any element of this Hilbert space is actually a holomorphic section, so I can evaluate it in points. And I will denote that evaluation by this guy. So this is a linear map from our Hilbert space to the fiber above X. That is also a Hilbert space, and this should be continuous for every point. So this, and then the third condition is that the adjoint of this map should be isometric. So this basically is saying that you can view the representation that we start with as a subspace of the larger representation, also in an H equivariant way, actually. Okay, so this is what we precisely mean by holomorphic induction. And why is it nice? It seems maybe a bit random to do that. So the nice thing is the following. So in this situation, there are two nice theorems that in this context can be found in the same article by Carl Hermann, and in finite dimensional case, I don't know who was the first. Anyway, the first theorem is that there is at most one unitary D representation holomorphically induced from such a pair. So you can really speak of the holomorphically induced representation. Right. So this is up to unitary equivalence, of course. And then the second main theorem is that you can also understand how they decompose. Namely, if I assume that rho is holomorphically induced from such a pair, and additionally that, and so as I said, I can view the representation I induce from as a subspace of the larger Hilbert space by looking at the adjoint of this epsilon at the identity. And that subspace should be invariant under the commutant of G. So this is equivalent to saying that the projection onto this subspace is in the von Neumann algebra generated by the representation. And in this case, then there is a map from the commutant of G to the commutant of this pair that we induce from, and I need to define that still. Anyway, the map will be defined just by restricting it to that subspace. And the claim is that this is an isomorphism of von Neumann algebras. So I will define this in a second, but first let me emphasize why this is so nice. First of all, we see that this induced representation is irreducible if and only if this one is irreducible. Or indecomposable would be better to say. And also it kind of says that they decompose in the same way. You can understand how this one decomposes as G representation if you know how this one decomposes. Okay, so what do I mean by this commutant? It is meant to be the involutive or star-closed commutant of this pair. So they are operators which first of all commute with the H action, but you additionally have that they commute with this psi in the sense, but not just T, also T star does. So if you're familiar with the representation theory of compact Lie groups, compact simple Lie groups, maybe it's good to notice that this is quite similar to the situation that you have there. So this is, there you have that a representation is uniquely determined by its highest weight. That is analogous to this statement. This is a generalization of that. And moreover, you also know that, so if a representation is holomorphically induced, then you know that the larger one is also irreducible. So these are kind of two key ingredients that you have when studying the representation of compact simple Lie groups. So if you now want to understand which representations are holomorphically induced, it basically remains to understand for which pairs does there exist a unitary representation corresponding to it. And for compact simple Lie groups, that would be the dominant integral weight. Okay, but as I mentioned at the beginning, all of this is based on this very strong condition. And I said it's quite rare to satisfy that. Oh, the minus is just not there. Yeah. Right. So now I encountered myself in a situation where I needed this machinery where this was not norm continuous. So I started to try to develop that. So that is the next section. Beyond bounded space. Okay, so what is the main problem that you have here? It is twofold, but perhaps most importantly, the construction of a complex bundle structure totally fails. So of complex bundle structure fails completely. So you need to come up with a way to fix that. And also you need to deal with unbounded operators. If you drop this condition, you no longer know that the image of this guy lies in a bounded operator. So you have to deal with domain issues, and it all gets a little more subtle. Okay, so in this article I propose two possible ways to deal with this, two solutions. One of them is more geometric in nature. So there I really still try to construct some homogeneous vector bundle for which the construction does work, but with smaller fibers. So you have not the Hilbert space on the fiber, but some locally convex space. And I replace this condition by a weaker condition, which is still very, very strong. So that's why it's kind of the downside of it. The upside is you still have this geometric nice interpretation in terms of holomorphic sections, but it requires, very strong assumption. On this sigma, weaker than that one, but still very strong. And then the second one is more general, but you lose the geometric interpretation. And the main point is that the construction still works, and you maybe shouldn't insist on the geometric interpretation. Or maybe you can try to recover it, but it becomes unimportant to the representation theory. Now with this cliffhanger, I will clean some boards. So what I want to do next is explain how you can overcome these issues in this less geometric way, the more general one. And then basically the result will be that the two main theorems still hold. And then if there's enough time. What? Then I want to also explain how it relates to this positive energy condition. I hope I have enough time for that. Need more space. Okay, so what did I do? The setting in which everything works is the following. We want now that this G, I want it to be connected. BCH Fréchet-Lie group. So this is like a slight generalization of being Banach. And what does this here mean? It stands for Baker, Campbell, Hausdorff, and it essentially means that G is an analytic Lie group, real analytic, and in addition, exponential map of G is an analytic local diffeomorphism in 0. So that is what that means. Okay, and then this closed subgroup H should be locally, well, still closed, connected locally. I want to specify exactly when it works, so now I have to introduce all these words just to be precise. Close, connected, locally, exponential. the subgroup. So what does this locally exponential mean here? This essentially means that you can use the exponential map of G to produce a slice chart for the embedded submanifold H. Provides a slice chart.
Yeah. What is a typical example?
Yeah, good question. So maybe I do that here. Example, the space of smooth functions on a compact manifold with values in a compact simple Lie group. But this is compact. So in particular, the loop group we saw yesterday. It is one example. But a non-example would be the diffeomorphisms on S1, for example. There everything fails. It's not analytic. It's definitely not locally injective. It's not locally surjective.
For the first example, no central extension or central.
If you had a central extension, it's still fine for either of these. It doesn't change any of these conditions. Pretty sure. I need to think about the analyticity. But, yeah. In any case, for this loop group, it is fine.
But what's wrong with diff S1? It's Fréchet,
So
right?
it's not an analytic Lie group. The exponential map is not locally injective and it is not locally surjective at 0. So everything fails essentially.
Is the typical example beyond the current groups?
Well, yeah, you can also have Al-Banach Lie groups.
Yeah, of course.
So I could probably come up with more, but yeah, let's stop here. Okay, let's see, where was I at? Right. Okay, and then I forgot to mention there, I want this representation to be analytic in the sense that the space of analytic vectors is dense. Okay. So now, almost done with the notation. I want to assume that the Lie algebra decomposes into 3 parts. And this is very much analogous with the positive roots, negative roots, and the Cartan, where you have some conditions. Okay, and then I define these B plus minus, and we saw one of them earlier, by accident. As the semi-direct product. So essentially, this part here would be B plus, this part here would be B minus. So that's analogous to the Borel algebra. Right. Okay, and then one more thing, I have the notation that okay, so now the idea is essentially to, instead of working with holomorphic sections, I look at the corresponding functions on the group level and try to formulate all the conditions there. And I kind of circumvent all these problems with complex structures. But you need to be very careful and do it in exactly the right way. So first of all, if I have a dense subset of this space of analytic vectors, dense in the sigma and also H invariant, then an extension of the sigma with domain. As I said, we now have domain issues, so that's why with this domain It's just Lie algebra homomorphism into the linear operators on this space. So it really leaves it invariant, such that, of course, it extends the original one. Okay, and now I need an analog of holomorphic sections. And then I can express what it means to be holomorphically induced. So as I said, the idea is just to reformulate it on the group level. It's a quite simple idea. So I define this space, which should be analogous to the holomorphic sections, to be real analytic functions from G to P sigma, satisfying the usual equivariance condition. So this then corresponds to, it defines a section of the associated vector bundle. And then I need something to correspond to it then being holomorphic. And that will be following some differential equation. This should hold for every V in this domain and for every I in V plus. So this is maybe not that intuitive, but it should correspond exactly to the Cauchy-Riemann equations that you have. Whenever the usual thing would have made sense, this would also have been true. And it specifies Cauchy-Riemann equations, essentially. Okay, so now I can say what I mean by holomorphically induced. So we say that rho is holomorphically induced by such a pair. If, first of all, I want, again, our Hilbert space to sit inside of the space of functions from, what was it, G to P sigma with this H equivariance condition. But I don't require holomorphic or anything, just maps. Such that, again, I want the point evaluations to be continuous. And then I want the adjoint of that to be isometric. The identity. Now comes the crucial thing that you get at by trial and error. You keep trying to prove this theorem and it keeps failing. So you keep changing the definition until it works. But it is a bit unintuitive, maybe. So I want this domain of the extension to be exactly those vectors which have the property. So this map here, I denote it by psi maps to f psi. And then using this guy, I can view phi sigma as a subspace of H rho using the adjoint of that one. Now I want the functions corresponding to these vectors to lie in that space. And that, yeah, so that is kind of the condition that you need to put that corresponds to the holomorphic stuff. How much time do I have? 1 minute, shit. Okay. I need to be very quick then. Okay, so maybe I will just say in words with this definition and the suitable adjustment of the definition of the commutant. Both theorems work, so I don't need to write it anymore. And maybe I can spend a little bit of time briefly talking about the relation with the positive energy condition, because that was kind of the whole motivation for me. But I will need to be more quick than I want to. So in this positive energy condition, you have additionally an action, and I will first simplify it a little bit by taking a torus action. So you have an action on G, which is a smooth action, and I want also G to be regular, whatever that means. And the subgroup H that I will consider will be the fixed points, but then the connected component of the identity. So we have a torus action on the group, so it will also define an action on the Lie algebra level by automorphisms. So I can decompose the Lie algebra into its Fourier modes, and I want that to define the same triangular decomposition. So essentially, these are the positive Fourier modes. These are the negative ones, and these correspond to the fixed points of the torus action. I would have made this more precise if I had more than 1 minute, but whatever. Okay, so now if rho is a unitary representation of, not of G, but of the semi-direct product, then I can decompose the Hilbert space into the isotypical components of this torus action. So and then I can call a representation of positive energy if only if the negative ones are all 0. So this of positive energy if this is 0 for all negative n. Okay, so that's one definition. I call it ground state if the I call this energy 0 level if this is cyclic for rho for G. So this means that the orbit of this is total, it spans a dense subspace, and it is analytically ground state. If in addition to this, we also have that its intersection with the space of analytic vectors is dense in the space. And then one more theorem I want to state, and then I'm done. So this is kind of the kind of object I was interested in. And it turns out to be true in this situation that the following are equivalent. First of all, rho is a ground state representation. Oh no, analytically ground state. And secondly, the restriction of rho, so-called rho is a representation of the semi-direct product. I can restrict it to G, and that is holomorphically induced from the representation that you have on this lowest energy, kind of this energy 0 subspace. With respect, I need to specify the extension, so this is with respect to the trivial extension. Okay. But I need one more condition, but I forgot to introduce notation. Yeah. Closed span. I can look at all vectors that are killed by the n minus. These are supposed to lower the energy. I look at all vectors that are killed by that, and then take the closure, and that should be equal to 0 subspace. It went a little too fast right at the end. I apologize for that. But this kind of ties together this holomorphic induction with the positive energy condition. And at the face of it, they appear to be very unrelated, but in fact, they are almost the same. So this means that you can study these ones using the two big theorems that we have before. So you can get results about irreducibility, about how they decompose, and all that using these theorems. Thank you.